last example problem is, in some ways, is the most interesting. It's the most general, really, or one of the more general ones that we'll look at. Let's look at the following situation. There was a figure drawn with this one as well, uh, in which it says, consider a straight line current carrying wire shown in a non-uniform B, where B is equal to B of x and the k hat, with B of x equal to this function, B naught and A, and both B naught and A are given constants. X is where it is. So I've got the current carrying wire on the x-axis from x equal to 0 out to L, so it's total length L. And the y-axis is in the plane, and that means that the z-axis is coming out of the plane of the page directly toward us. And the thing that's interesting here is it's a straight line segment, so that's fine, but I can't use the straight line segment because that only works for a uniform B field. And here I've got a non-uniform B field. In fact, there is the weakest portion of the field, assuming B naught and A are both positive. At x equal to 0 here, that would be along this axis anywhere. At x equals 0 along that y-axis, x is 0, and so I get this expression for B, and B is going to be positive coming out at me. It's in the k hat direction, but it's very weak, and so there aren't many field lines coming out of the page at me. But as x increases, so I go x increasing over here, I go a little further into it. Well, now I've got a positive number times A, and so this whole magnitude. So in this region, the field is increased, and I put another field line coming out of the page. In fact, as you go to increasing x, the field lines are going to be denser and denser. There's going to be more and more of them coming out of the page because the field is getting stronger as I go from left to right coming out of the page. Well, because the magnetic field in this case varies with position, I can't use the uniform straight line current carrying wire in a uniform magnetic field. In fact, what I have to do is I have to go to a small segment of it, dx, here, that's located at distance x from the origin. And in that region, if dx is very, very small, then over that portion there, B is effectively like a constant. And so the magnetic force on just this small segment here is I times the dl vector crossed into B, where B is the field at this point, and dl vector is going to be dx in the positive I hat, the direction current's going. And I think I've written that out. So dl vector is dx in the I hat, length dx, and it's pointing in the same direction as the current flow. And then B, well, we were given what the magnitude of B was. It was B naught plus AX. It depended on the position, and it's all in the k hat direction, so it's this. Again, it's a function here of x, but as far as the vectors are concerned, it's a constant, so I can pull that through. I can pull out. The B naught I can pull out. I'm left with, and the dx I can pull out. So basically I pulled out in front all of these quantities, and I'm left with I hat cross k hat. And I hat cross k hat is minus j hat. So the infinitesimal force on just this infinitesimal piece at this location is given by that expression. And now then I want to add up all of them from x equal to 0 to get the infinitesimal pieces down here, the force on it, add up all of them till finally you get to x equal to L. And so I have to add up all these df's from x equals 0 to x equal to L, which gives me this integral here to do. Again, I can pull out some constants. Minus I can pull out. The j hat you can pull out. It's a constant unit vector, but I can pull that outside the integral. And then I'm just left with this basic integral to do, which I did. That integral is b naught x plus a x squared over 2, and I have to evaluate it from x equal to 0 to x equal to L. The upper limit at x equal to L is this. The lower limit at x equal to 0, well, the zero's in there, this all goes out. And I get this expression. Or if you wanted to, I guess you could pull out a common factor, L here. Notice it's going to be in the negative y direction. So all of the force on this is going to be downward on this page in the negative y direction.